So we're going to start on page 13. Just a couple of announcements before we begin on page 13. So first is our usual look at the calendar. So today is our fourth class, and this is the fourth and final class of what I'm calling numerical literacy. So let me just remind us briefly of what we've done so far in our three classes. In the first day, we talked about problem solving, and we counted pennies that fit in this room. On the second day, we did the order of magnitude estimations, like how many cobblers make their living in that profession here in the US, and how many dentists are there in New York City, and how much water have you had to drink in the last decade. Those are all called order of magnitude estimates. And then last class we talked about percentages, and you guys worked really, really well. I appreciated that last time on the problems with percentages. And today we talk about working with large numbers, and there are a lot of places where we see large numbers outside of a math classroom, which is why I think it's important to talk about in the math classroom. And that's the end of the first four classes. And then the next four classes, next four classes are all about something called voting theory. And here in 2012, it's a presidential election year, right? Primaries are happening, and so I think it's very appropriate that we'll spend some time talking about voting theory. And so that's those four classes coming up. One not related to math announcement. On the main GCC webpage, you will find a link. Let's scroll down just a tiny bit here. There's a link to something called the 2012 Foundations Scholarships. Has anybody gotten any of these scholarships in years past? Yes, one? Okay. So I know that there are like a million different scholarships out there for you to apply to, most of which you are not eligible for, most of which you are competing with people from across the country or across the world. I will tell you that the scholarships that are in this, so there's the scholarship description page. These scholarships are given to GCC students only. So the people that you are competing with for these scholarships are the people in this room and the other people in this building, and that is all. There are about 2,500 GCC students, most of which will not apply for any of these scholarships. You will never find better odds in terms of money for not too much work, right? And I'm not going to go through all of them, but you can take a look and you'll see that there's a whole long list of scholarships that are being given out. And I just want to point to a couple just to give you a sense of like who's eligible for these kinds of things. So we can look at the first one, for example. This 25th anniversary scholarship, there is one award for $825. That feels like real money to me. I don't know about you guys, but one person is going to get this. One GCC student is going to get this, regardless of how many people apply for it. Any student, full-time or part-time, is eligible, and it's on the basis of scholarship, financial need, and character. And all you need to do is fill out like a sort of simple form to apply, and you need to get a recommendation letter from a faculty member or a clergy. Mary, do you remember, was there anything else involved in your application process?
A letter kind of explaining what it was, where else.
Mm-hmm. Yeah, and did it seem like was it a drawn out process, lots of forms?
Instructions were very simple, specific.
And if you have to apply, if you want to apply to several awards, do you need to do like several things, or is it just a matter of like clicking the boxes and say, I want to apply to these 6 things? Is that right?
Yeah.
For most of them. Right. Right. I think that most of them, it's an easy matter of filling one application and then saying, I would like to apply to these 6 awards. But some of them are more specialized. And so you would need to kind of say, yes, I live in, I live in Franklin County. Like that's one of the requisites or something. So that's that one. I'm going to show you 2 more. Here, this Jeffrey Bond scholarship is $550, given to a female student to help her make a transition to academic life, and who sees a GCC education as one which will allow her to move on to a new career or to pursue a higher degree. Some of them are more specific. We just eliminated half of the population here, right? So half of you are happy and half of you are unhappy. But I'm just saying that like there are different awards here with not just 2,500 people, but narrower and narrower portions of this population. Absolutely. Last one I wanted to look at, this one at the top, another $850. It's for an outstanding student in business or a business-related major. So you just look through, and I guarantee you, you guys are eligible for a lot of these, and some of you are eligible for these really tiny ones, not tiny in money, but tiny in terms of how many people might end up applying for them. So if you can kind of find a niche that, you know, it's like you and 10 other people at GCC will apply, you might be the only one that does. So anyway, just putting it out there. I don't know when the deadline is. I'm sure it's here. Anybody see it? Thank you. That was on the other page. Yeah, thank you. March 9th is the deadline, and I don't believe it's a lot of work to apply. You're welcome. Just on the main page. Good question. I am now recording the audio and everything that happens on the smartboard in a video. I was only able to start doing this because we had some technical issues with the Bluetooth, but it should be working. I will show you next class what it will look like, and then I'll let you know how to access these videos if it's a resource that might help you study for tests or go through things to look at homework.
So we'll record what's happening on the thing, and then we will see the video from Blackboard.
Yes.
Or I mean from Google and hear your voice recorded.
Exactly. Exactly. Everything that's on the smartboard and everything I'm saying will get recorded in a video that I think is a good resource if you miss a class, or if there's just some part of the class that went a little bit quick, but you didn't want to ask a question in class, you just go take a look at that part of the video. But I'll show you exactly what it looks like on Thursday. All right. Okay, on page 13, we'll start here in the middle with number 1. And maybe we can begin with, oh, I don't know, Charlie.
10 to the 6th.
Start up here.
Now begin our study of large numbers. The goal of this section is to increase our numerical literacy and comfort with big numbers.
Okay, and then a quick review of scientific notation. So quick that I'm not going to do it. Can you guys fill in with the people? Check with the people at your table, see if you can fill in the blanks with all of those zeros and all of the names of those big numbers. Okay, let's get some names up for these large numbers. So somebody from this table here in the middle, what is the name of 10 to the 6th? That is 1 million. And somebody from the table in the corner by the door, 10 to the 9th, what is the name of that number? Close? Yeah, 10 to the 9th. What is that number right there? It's 1 billion. Yeah. Okay, and somebody in the other corner, 10 to the 12th trillion. At some point, these numbers become like so astronomically large that they're hard to conceive of. I might argue that that happens at 1,000 already. It's hard to visualize 1,000 something. Certainly 1,000,000 somethings I don't know if I've ever seen. But trillion, is there any place outside of a math class where like trillion is the what the national debt, isn't it on the order of trillion? So like there are numbers that get as enormous as these things. Okay, 10 to the 15th. How about this table up here? You guys know the name of that one? Quadrillion. Very good, Henry. Quadrillion. And did anybody in this group know the name of 10 to the 18? Quintillion. Excellent. There actually is some order to this list. If you skip over the million part, but if you just look at the prefixes, what does bi mean? 2. Tri is 3. Quad is 4. Quint is 5. The prefixes make sense. I think it's sextillion is the next one. I think so. Okay, let's go to number 2, and I think we're up to J. Oh, yes. Excellent question. It's a good point. You'll notice I glossed over the zero stuff that Jocelyn has called me out on. I just said it makes sense in terms of the order, right? The order makes sense. Okay, I do think that there is a rational explanation for this. Phil, do you know?
Well, because we're going from 1,000. So if you take it from 1,000, million would be 1 extra cent. Suppose million would be 2 extra cents.
Yeah, so maybe like the 1,000 is like the base number. So if I cross off like the last set, oops, not that one. Like if I cross off the last set of 3 zeros, then at least it matches with what Jocelyn wants it to be in terms of the number of sets of zeros. Anybody here speak Spanish? What's the like this number right here with the 6 zeros? What is that in Spanish? It's the same, and 9 zeros is it's the same. Is there? I really thought there were some languages where the numbers were different. Is anybody? Yeah.
Well, in Sweden, 1 billion is 1 milliard.
Okay, so what we are calling, so what do you guys call this number in Sweden?
Billion.
Okay, and then the next number?
Billiard.
And the next one?
Billiard.
So that matches the trillion, yeah. I really thought there were some languages, and I actually thought Spanish was one of them, but I guess I'm mistaken. In French? Do you know the numbers in French? Yeah, I really think that English is kind of an outlier, and a lot of places in the rest of the world match up with exactly what Jocelyn wants the names to be. That the number of sets of zeros matches the prefix. So for this trillion here, I think that there are some languages in the world where you get 3 sets of zeros. But that is the number trillion, whereas here we call it billion. I actually I thought Spanish, but I guess I'm mistaken.
Well, it's just
Yeah. Mhm. Yeah. Yeah, and maybe then I can jump on board a little more with what you were saying with the first 1,000 is like taken care of with the meal part.
Yeah.
And that's just sort of off the table, and then we just look at the remaining zeros. Yeah, good question, Jocelyn. Mm-hmm. What page are you on in the page number 1? Yep.
Well, but that would be so different because in some countries they use points instead of commas.
Can you show me, Wadada? Where are you? Oh, in the side there. Yes. Yeah. So 1,000 trillion is 1,000 billion, 10 to the 12th. Yeah. So yeah, if you look on the first page, Wadada has found this little note off on the side here, kind of talking about some of the stuff that I have vague recollections of, but it's not right there for me. But the same this idea that there are a lot of places where the numbers that we use don't match the numbers that some other countries use, or the names that we give them anyway. Thank you, Jocelyn. Okay, let's go to number 2 for Linda. Any Taylor Swift song fans in the room? Yeah, a little bit. Yeah, there are more of you out there, even if you don't want to admit it. I mean, she was the most highly played artist in 2 years in a row. I don't know who it was in 2011. Maybe it was her again. Okay, let's go to Linda for that next number. Yeah, sorry, Mary.
300 billion.
Good. Good. Next page. Let's go to Johannes. Just read that number at the top, if you would.
Oh boy.
Good. That's right. So we talked about trillion being on the order of magnitude of the national debt. That's good. I will read this next number. That is 43 quintillion, which is the number of different ways you can mix up a Rubik's Cube. Number of different positions of the Rubik's Cube. All those different scrambles, there are 43 quintillion and change. It's not exactly 43 quintillion. Okay, the next number I won't bother to read, but maybe somebody can describe what it is. We'll go to Kelly. Could you just read the description? Avogadro. Okay, so imagine something that's like a gram, so like a little tiny thing here, but you can visualize the gram of stuff. If that gram of stuff is hydrogen, then the number of atoms, these little teeny tiny like I can't even imagine like specks of things. There are this many of them in this little gram of hydrogen. I think that there is more detail in this definition than I'm giving. In physics, like constants used to be simple things like this, but they've become more and more detailed. And so really maybe it's something like the number of hydrogen atoms in a gram of hydrogen at 30 degrees Celsius at an altitude of 300 meters, you know, like all the details. It's a good point. Okay, this next one here, 0.0, well, lots of zeros and then a 2, which is a very small number, very close to 0, is the number of seconds it takes for a modern desktop computer to perform one floating point operation. So if you wanted to type into the computer, you know, how much is 85 times 63, it would take like this long to do a little calculation, one little calculation, which is not very long, which is why computers seem so ridiculously fast. All right, we go to number 3 and Iris. Okay, so you can see the struggles that we had even to just read these numbers out loud. So scientific notation comes in so that we don't have to read and translate all those zeros. And let's take a look at this example here. A lot of different ways to write the number 230. You could think of it as 230 times 1, which is 230 times 10 to the 0. It's kind of weird, but anything to the 0 is 1. It's like a definition. Or you could think of 230 as 23 times 10. Agree? And that's really just 23 times 10 to the first. Fair enough. Or you could think of 230 as 2.3 times 100. You buy that? And that's really 2.3 times 10 squared. And so that last number is actually what we call scientific notation. We'll talk about why that is, but really what's happening here is something about moving the decimal point. I'll put the decimal point in. For example, it is currently right here. If you decide you wanted to move it to right there, you need to kind of pay for it. And you pay for it by putting the right power on the 10 at the end. So let's go to, Iris, did you read? Yes, you did. Brittany? Okay, so here's how you get something in scientific notation. You figure out how many places you need to move the decimal point to the left, however many places you had to go, you put 10 to that power on the top. And how do you know when to stop? You stop when the number that you end up with is between 1 and 10. 2.3 is the number that I ended up with. Is 23 between 1 and 10? No, which means I didn't go far enough. You have to keep going until you get something that is between 1 and 10. And as Brittany reads, said a different way, how many digits are to the left of that decimal point? Just 1 in the end. There's only 1 digit to the left of the decimal point. In the number 23, how many digits are to the left of the decimal point? 2. That's too many. You got to have 1 and only 1 digit left of that decimal point. Madonna. Yeah, 10 is 2 digits. What did I say here? We repeat this process until the number is between 1 and 10. How about we say strictly less than 10? Is that better? Okay. That's a good detail. Strictly less than 10. Okay. Let's try number 4, and we'll go back to Justin. Okay, can you guys try that and check with your neighbors? Okay, so let's come back together. I heard some right answers right away. The decimal point is currently at the end here. I've put it in. You need to get it to go, oops. You need to get the decimal place to go left. 1, 2, and then finally 3 spots. We needed to get to 8.6. And so 8.6 times 10 to the 3. Questions on that? Okay, let's go to Doug for number 5. Okay, can you guys try that? All the numbers from the previous page and the top of this one, and check with your neighbors. So I have a question for you guys about this first one. True or false? This equals 12.3 times 10 to the 12th. Is it true or false that those numbers are equal? It's true. It's true. It's not what? It's not in scientific notation, which is okay, but it's true. A friend of mine who also teaches math, he thinks that scientific notation is not appropriate because 10 to the 13th is not something natural, right? It's just, we just put it up there because we have this artificial, that's what he wants us to use. What can you tell us about engineering notation, Johannes?
Move the decimals to the right. It's really more simple.
Yeah.
That's what I know.
Yeah.
I just briefly glazed over
Yeah. So engineering notation is what my friend Phil thinks is better. And engineering notation means the power on the 10 is supposed to be divisible by 3, which seems like a strange thing at first. But if you think about it, it actually makes a lot of sense because we have names for all these things that are divisible by 3, right? Every one of these powers has a name because it's divisible by 3. So, so down here, instead of saying 3 times 10 to the 8th, where I have to sit here and scratch my head, what is 10 to the 8th again? I need to think about listing zeros. I have to like translate it to figure out what it is. Engineering notation would say, actually, let's write that as something times 10 to the 6th. In this case, it's 300. And so if I'm in my head, I know that 10 to the 6th is a million, and that's something that I know, then this is immediately 300 million, which is a whole lot easier to me than 3 times 10 to the 8th. Just putting it out there. All right. What about engineering notation? Did you? Good. And there's a good reason for it. It's because these guys have names and they're just more natural to us than 10 to the 8th. Okay, thank you guys. Let's take a look at number 6. And where's our reader now? Is it Zach? Okay. All right, so let's try this guy. This number is very close to 0. The decimal point in this case still needs to get to the same spot. It's going to be 4.6 when we're done. That's the goal. It's always between 1 and 10. So the question is, how many places does that decimal point need to move to get between the 4 and the 6? It's 5 places. So this number right here is equal to 4.6 times 10 to the, it's negative 5. Yeah, that negative means we're going the other direction. The negative up there as a power means that number is quite close to 0. And there are lots of places where numbers close to 0 are important. For example, if in this little tiny gram of hydrogen we were talking about, there were an enormous number of little atoms floating around, well, gosh, they must be pretty darn close to each other. So maybe a number like this would be like how many millimeters they are from each other as they're floating around inside here. So lots of things in chemistry have to do with small numbers, close to 0. All right, number 7 says go back up and write the number from the computer example in scientific notation. Can you guys do that for this last number? And check with your neighbors. And it's 10, and it's 10 going left, so it's negative. And I'll just highlight, oftentimes people get confused and they think scientific notation involves counting the zeros, and that's what goes up there. How many zeros are there? 9, but that's not the right number. It's how many places do you need to move that decimal point. So a lot of times it's not anything to do with the number of zeros. It's always how many places does it need to move.
There is a 0 to the left of the area you still see.
Yeah, oopsies. It's true. There is a 0 out there to the left. Yeah, there are plenty of zeros in here, right? Counting zeros is not a reliable way to do scientific notation. Okay, so this is good, and let's go down to number 8, and I think we're up to Ashley. Could you read number 8? Thank you. So if you ever type something into the calculator and you see an E, I want you to know what it means. And it means times 10 to the whatever number you see next, okay? So if you see 4.1E8, it's the calculator's way of writing scientific notation. The E stands for exponent, and it's always an exponent on the number 10, just like we do in scientific notation. Alex. I don't know why they don't just put 10. It seems like the displays right now are, it's easy enough to put 10 to a power. I wonder if it's, I wonder if it historically was because the calculators couldn't display powers before, you know, the early calculators, but they could display an E and they could display an 8 right next to it. So I wonder if that's just like a historical remnant because of the pixels. Yeah, yeah, E stands for exponent. So if you have a calculator on you right now, I just want to make sure you know how to read this or interpret this. I'll do this on 2 different calculators. So if you happen to have one of these kind of calculators on you, you see right above the comma it's hard to read, but in yellow is EE. I also don't know why there's 2 of them, but that's the button that says times 10 to the. So if I type in 4.1, and then I find this yellow button, so I got to hit the yellow thing first. You see it says E. And then if I hit an 8, it's telling me, okay, I know what that number means, all right? And then on this calculator, let's see, is it the same? Anybody see an E button on this one? Where's the EXP? Here? Let's try that. 4.1, I don't know. Oh, that looks good. 4.1 E and then positive 8. That's not an add 8, it's a positive 8 as opposed to some of these numbers which have a negative power on the 10. And I think if I hit enter, it will tell me the same thing we saw before. Right? It's not super important to me that you can type that in, but what is important to me is that if you're typing stuff in and the calculator gives you something with an E, that you know what's going on. So if I just type in some crazy big numbers multiplied by each other, like, what does that mean? That's what I want you to get out of this. It's not how you type the thing with the E. You could just type zeros if you have patience. But that number means something, and it doesn't mean anything close to 1.8. What number is this really? It's 1.8 times what? Times 10 to the 12. That's what that is. It's 1.8 times 10 to the 12, which is in the trillions, right? This number is not anything close to 1.8, but if you don't know what's going on with this E, you just don't know how to interpret it. This is how we interpret the E. Questions on?
Did you say you don't know why it's a double E?
I don't know why there's 2 E's on the calculator. Yeah. Justin. Yes, perfect. We'll just add some zeros if you run out of numbers that you see. Good. Okay, let's try number 9. And are we up to, is it Hillary? Okay, so I think we did that. And we'll go back to Sam for number 9. Go ahead. Okay, so 130 million is a number that I cannot conceive of. Conceive, yeah. So it's just so big that I just can't imagine. 130 million babies are born every year. I can't picture it. I can't do it. But maybe we can get that number down to a more manageable size. If I were to take this year-long number, which is enormous, and maybe shrink it down to how many babies are born in a minute, maybe I'll get a number that's small enough that I can imagine in my head. So let's give this a shot. There are different ways to do this, and if you have a way that's a little different than what I'm going to show, then stick with it. I don't need to force anybody to do it this way. But if you're not exactly sure how you would do this kind of thing, I'm going to give you a method that I think works every time. And so here's what we're going to do. We have 130 million births per year, and per means division, right? So that's how we can write 130 million births per year. And ultimately the goal is births per minute. So we're going to do something that we like to call unit conversion. We're just going to convert from years to minutes. And the way that you convert is to multiply by 1. What happens to a number when you multiply it by 1? Nothing, which is the only reason what we're about to do is legitimate. I'm going to multiply this number by 1, which will not change it at all, but it'll at least make it something that's in a better form for us. I'm going to multiply by a fraction. I don't like years here. Would you rather put years on top or bottom if you want to cancel with the ones that are already there? I want to put it on top. And then we're going to convert from year to some smaller unit of time. You could go months because there are 12 months. The difficulty in going months is that the months don't have the same number of days in them. You could also do weeks. How many weeks are in a year? 52. Is that true? Yep. Are there 52 weeks in a year?
Not every year, not exactly.
Are there 50? This is something we know, right? 52 weeks in a year. Have you ever thought about checking that? 52 weeks. Don't write this down. 52 weeks. How many days in a week? 7. Multiply this. 364. Are there 52 weeks in a year? A leap year is even worse. Leap year is 366 days, right?
Why are we multiplying by 364?
Well, that's why this is not a good idea. There are not 52 weeks. What's that? Yeah. That's right. So it's complicated by the leap year stuff. But 364 is never the right answer, correct? We know there are 365 days in a year. If you have a calendar, you go count, you will get to 365, unless you're in a year like this one, which is a leap year. How many days are in this year? 366 is an extra one. 364 is not right, which means 52 weeks in a year is false. So let's not introduce error where we don't need to. So how about instead of going months or weeks, which both have problems, we go days. How many days in a year, not counting leap years? 365. 365 days in 1 year. Talk to your neighbor about the value of that red fraction. What number is that red fraction really equal to? Talk to your neighbor. How much is that one fraction equal to? Hold up the number of fingers that is what this red fraction equals. That red fraction equals 1. Yes? You can't ignore the units here. 1 and 365 are just numbers, but these have units. 1 year is exactly the same as 365 days. When you have a fraction where the two things are exactly the same, what is that fraction equal to? It's equal to 1. If the top and bottom of a fraction are the same, your fraction is equal to 1. So why is it okay to multiply by this? Because multiplying by 1 doesn't change anything. I still have 130 million births per year, but now it's going to be in a slightly better form because I can cancel my years. We'll play the same game. I'm going to write down some units. You guys are going to fill in the blanks with the numbers. We can go from days to hours. And then there's one more fraction you're going to want to introduce. Eventually we need minutes. Births per minute was the goal. Check in with each other, see if you can fill in those two numbers and the last fraction, and then we'll get our final answer to this problem. Okay, so I've got my units up here and I've crossed out lots of stuff. I just want to highlight, generally when you do this kind of thing, you put lots of ones. You put ones wherever you can. So, 1 year is 365 days, 1 day is 24 hours, 1 hour is 60 minutes. Ones make it easy because you know what these numbers are by heart. And if you put the units in the right spot, you can see they all cancel in green. And so ultimately what we're left with is births per minute, which is the goal. So now let's finally get the answer. I'll go ahead and write it in, I'll write the units in, but then we need the number. Okay, some number of births per minute. I'll type this on my calculator and then we'll get our answer. Okay, so we started with this 130 million, so that's the first thing I need to type in. You know the really funny thing about this calculator? Did I tell you it goes into power save mode? Did you see that? Have I mentioned this before? Yeah, it's a great feature, right? Your calculator shuts off after 5 minutes. So does mine. The problem is mine has no batteries. Why does it shut off after 5 minutes? It does a good job. Okay, 130 million. Okay, if you feel like it, hit a bunch of zeros after that. I prefer not to do that. I'm doing my E business. How many extra zeros in million? 6. I just find it more accurate. It's not even about time. It's not even about saving time by hitting zeros. It's really easy to hit one too few or one too many, and then it's really hard to see it. You have to look at it really carefully to see that you've made that mistake. I like to do this.
If we were to see numbers like this on a test, you just have to do the engineering or
Here we're just typing it in, and you can type it in however is convenient for you. I'll be really clear. If I want an answer in scientific notation, I will say, give me this in scientific notation. If I don't, you can write it however you want. Okay, 130 million. Then we're multiplying by 1 divided by 365, and then we're multiplying by 1 divided by 24, and finally 1 divided by 60. We crunch all these numbers together and we'll get the answer. 247 births per minute. Alex. Mm-hmm. Yep, perfect. Yep, that works. And like I said before, if you have a different way, it's not exactly this, no problem. I'm just giving a way. If you're not sure what to do, I think this is a natural way. You write units down because you need to cancel other units. But if you've got some other method, as long as you get around to this 247, by all means use it. Okay, so we'll say around 247, and you know that's close enough to 250. We don't need to get lost in the detail. About 250 births every minute. I can imagine that. I can't imagine 130 million babies, but I could see 250 every minute. Questions on that one? Per second is how many? Yeah, so divide by another 60, I think.
So it's 4.16 babies.
Every second, about 4 babies are born across the world. I can imagine that. No? Okay, so that's this one. Let's go to the next page. We're going to skip part B. It's about Twitter and when Osama bin Laden was killed. But it's the same kind of question, so maybe come back to that one later. We're skipping down to this matter of scale business. So we've talked quite a bit about large numbers. We've seen like Taylor Swift and other kinds of large numbers. We talked about scientific notation. And then finally, we talked about taking a big number like 130 million births in a year and scrunching it down to something manageable, 250 births every minute. Now we're going to take a different tact. We're going to look at scaling things. You guys have seen like scale models of trains, right? Or a scale model of like some set of buildings, like a city or a town or a house or something. And the basic idea with scaling is that you take something that's quite large, like this train set, not train set, like an actual train, like a bunch of trains all stacked together, and you shrink it all down, but you make sure you keep the same like proportions, right? If the caboose is like half the size of the engine in reality, then when we shrink them both down, the caboose is still going to be half the size in the model. Johannes.
So if you wanted to do exactly their first class, you might make a model of this classroom, and then take a bunch of tiny copper points and try to make that a bit easier than just. You couldn't fill this room with pennies.
Right. Yes, so you could maybe imagine making a scale model of this room real small and then scale pennies, and then maybe throw them in there, and there should be still about 300 million of those scale pennies would fit in the scale shrunk down version of this room. All right, so places where scaling down is really important is in outer space, because things in outer space are just like unbelievably far apart. What is most of space? What fills most of space? Nothing. It's just darkness. There's nothing going on in most of space. And if you're like stranded out there someplace in space and you want to go for the nearest star, it's going to be really, really far away. Like so far that like it boggles your mind how far away these things are. So what we need to do is we need to get our mind wrapped around something. We're going to shrink the universe down to size. Shrink it down so that I have some idea of how far apart these things really are. Okay, let's start with our next reader. I think we're up to Jocelyn. The following table. Okay, so first of all, light year sounds like a unit of time. It's not. It's a unit of distance. It's deceiving because year is a unit of time, but a light year is a distance. It's how far light can travel in 1 year. It's really far, right? Light can travel really, really fast. So if you let light go in a straight line for a year, it can go an incredible distance. 10 to the 12th, that's trillions. It can go in the trillions of kilometers. Really, really far. Okay, here's a list of some stars. This is the brightest ones from our perspective here at Earth. Obviously, the brightest one is the sun. It also happens to be the closest one to Earth. And it is 1.58 times 10 to the negative fifth light years. I don't really know how to comprehend that. Does anybody know how long it takes light to travel between the sun and here? Sometimes some folks just have this number in their head. 8 minutes is correct. It takes about 8 minutes for light to travel from the sun here to here on Earth. So for example, if we were standing outside, I think it's kind of cloudy, but imagine the sun was out right now and we were standing outside and there was some catastrophe and all of a sudden the sun imploded and it just disappeared. What would we see on Earth? Like we're out there, right this moment the sun implodes. What would we see? We wouldn't see. That's right. We would see no change for 8 minutes because the light that you are seeing right now, the light that is hitting this building is 8 minutes old. The light that is hitting here left the sun 8 minutes ago, and if the sun were to implode, we wouldn't notice any change for 8 minutes, and then all of a sudden it would be like, who turned out the lights?
What about stars? Like they're really far away. They have been dead for a couple days.
Mhm.
The light year away, it takes a year for the light.
Right.
That's right. And so it's,
Like really different stars.
yes, yes.
That's very scientific.
The stars that are in the same place as you see in the night sky. It moves too. Like,
Yeah.
So.
Yeah, so this is a really good observation.
Every star is dead.
It could be. It could have been dead for like since before, Earth existed. Like it's just so strange that when you look up in the, at the constellations, you are looking into the distant past. You're looking at things that existed before the dinosaurs. Like the light that you see from those stars is from before the dinosaurs even roamed the Earth. It's just so far away. It takes so long for the light to get here. You are looking in the distant past. And so it could be that there's been some apocalypse out there that we have no, like, we're not even going to, we wouldn't know. We're not going to know until the light finally gets here. Could be for, like, essentially forever away from now in terms of when we find out. All right, so the sun is this many light years away. It takes about 8 minutes for the light to travel. But the light getting here from Alpha Centauri takes about 4.4 years. This star right here, the light that we see, if you look up at that star, Alpha Centauri A, it takes 4.4 light years, 4.4 years for the light to get from that star to here. And you can see Sirius and Vega and all these other ones, Rigel, 770 light years away. If you see Rigel up in the sky, you're looking at something from 770 years ago, right? And you imagine 770 years ago, I don't know, like the Magna Carta, right? Like one of these like famous document, like when the Magna Carta was being signed, there was light that was coming from Rigel. And now eventually today, we see the light that was happening, that was started when the Magna Carta was being signed. All right, so let's suppose that we're going to try to shrink down the universe and make it so it's a scaled down version of things, scaled down model. All right, let's go to Alex. Suppose. Okay, so when we say like a model train is shrunk down, sometimes you see something like 1 to 500. What that means is that whatever the original length and distances were on the train, when we get the model train going, everything is 1/500th of the size it used to be. So you might see that kind of like, it'll say 1/500th scale. The same kind of idea here. But if we bring everything in so it's 1/500th of the distance, it's still going to be astronomically far away. So we need a really, really tiny scale factor. Not 1/500, but 1/1 quadrillion. That's how we're going to try to shrink things in so we can understand how far apart things are. Let's go to Holly for number 1.
How far apart is the Earth and the Sun on the scale? Call that the Earth-Sun distance of 150 kilometers. We'll probably want to
Okay, so let's give this one a shot. How far is it from the Earth to the Sun in this scale model? Okay, so we start with the original distance, 150 million kilometers. This is how far apart the Earth and the Sun are in reality. We're going to shrink it down. We're going to shrink it down by 1 to 1 quadrillion. Multiply by 1 over 1 quadrillion. And that's all we have to do in this case. This is how you shrink things down, is you multiply by that kind of scale factor, that 1 over 1 quadrillion. So I'm just going to type that in and we'll get some number. And of course, we're on power save mode. Okay, so 150 million. Again, I like my E button. Saves me some typing. Divided by 1 quadrillion. How many? I'm kind of ignoring the 1 over. I'm just dividing by the number on the bottom. 1 quadrillion. How many zeros in the quadrillion? 15. Six. That's the million.
Oh, yeah.
Okay. All right. 1.5 e negative 7. Okay, I can write that. So this thing here equals 1.5. We do not write e. E is calculator speak. What do we write? Times 10 to the. Write e, write times 10 to the. Okay, what are the units for this answer? Well, what were they before? What were the starting units? Just kilometers. What are the ending units? It's still kilometers. Just like your train could originally be in feet, and then you shrink it down, it's still feet. This is still kilometers. It hasn't changed. But that's not a very useful number. 1.5 times 10 to the negative 7. I can't visualize that. All right, here is where the fact that we are terrible at the metric system is going to haunt us. Do you guys know how to go from kilometers to meters? There's 1,000. We could Google. Google knows how to do it. That's true. Let's 1.5 times 10 to the negative 7 kilometers. I'm going to play my same game. I've got meters in a kilometer. How many are there? 1,000. 1,000 meters in 1 kilometer. And the reason this is a good thing is that 10 to the negative 7 is such a tiny, tiny number, I'd really like to beef it up. This will beef it up. Okay. If I multiply those, you could check on the calculator. It's also a simple matter of saying, well, I just gained 3 zeros. So what am I at now with that negative 7? It's at negative 4. You could type it if you want to. But you were at negative 7. You just gained 3. So now we're at negative 4. 1.5 times 10 to the negative 4. What are the units now? Meters. Okay, at least it's more manageable. Still, 10 to the negative 4 is quite small. Do you guys know how many millimeters in a meter? That's also 1,000. Isn't the metric system fun? 1.5 times 10 to the negative 4 meters. That's what we currently have. I'm trying to get to millimeters, so I'm putting that on the top and meters on the bottom. We said 1,000 millimeters is 1 meter. (1.5 times 10 to the, I had negative 4. I just gained 3 good zeros. So what am I at now? -1. If you don't know how to do that, just type it into the calculator. No problem. This is currently millimeters. I think this is good. Yeah. Because times 10 to the -1, yes, is really 0.15. Okay, so first recognize, I'm not going to ask you to do tons of stuff in the metric system. I'll probably just let you stop with this first answer, 1.5 times 10 to the -7. It's just not a very useful number, which is why I wanted to do this, so we could visualize it. But on a test, I'd probably just say, okay, convert, you're done, it's fine. 0.15 millimeters is the distance between the Earth and the Sun in the scaled down version, okay? The Earth and the Sun are however part they are in reality. We're shrinking the whole universe down. Currently, in our new model, the Earth is here, Sun is here. They are 0.15 millimeters. A millimeter, you can visualize it. It's got a little bit of thickness, but not very much. And you don't even have a whole millimeter. You have a little fraction of a millimeter. So I can't push my fingers together that close. But basically, the Earth and the Sun are on top of each other. But now to put things in perspective, we need to figure out, well, where's the next star? You know, like if the Earth and the Sun are right here, is the next star like an inch away? Is it a foot away? Is it miles away? This is how we can kind of start making comparisons with these things that are so far away. Okay, so here's what we do. We'll go to the next page, and we'll try number 2. And Holly, you read already, didn't you? Emma? Okay, let's think about 1 light year. I gave you a fact on the table there. 1 light year is how many kilometers? Okay, so that's our fact. That is a light year. It's in the, I think it was right at the top of the chart. Yeah, right above the chart. Okay, so, well, that's a really big distance, and I can scale that distance down in our scaled version of the solar system. So 9.46 times 10 to the 12th. Well, let's see. That's the big number. In this version of things, what do we do whenever we want to scale down our big number? You multiply it by this 1 over 1 quadrillion. That's what we're going to do to every number to shrink it down in size. We started with a bunch of kilometers, shrink it down with this 1 over 1 quadrillion. We do the same thing right here. So I'm going to put it in red again, times 1 over 1 quadrillion. Now, how many zeros was it in the quadrillion again? It's 15. You can type all this stuff in if you want. One nice thing with a little bit of practice, scientific notation calculations can become pretty straightforward. If there's 15 on the bottom and 12 on the top, it's a -3 in total. Some of you guys can already do that. I'll never need you to do that. You'll have the calculator in your hand the whole time in my class. But anyway, that's the number. What are the units? It used to be kilometers. It's still kilometers. Scaling doesn't change the unit. So 9.46 times 10 to the -3 kilometers. Okay. Yeah, let's try that. Again, not going to ask you to go this extra step, but I'm just trying to visualize how far apart things are in the universe. So if I wanted to go kilometers to meters, we're multiplying by 1,000. I won't write the details, but this is exactly 9.46 meters. Is that right? Yeah.
When we do this problem though, like if you say you had us write all this out, do we actually need to have the meter step, or can we go straight?
You could go straight to millimeters if you wanted. Yeah. No, I think it's good. Like generally you convert until you get something that's reasonable. And I would say that I can visualize 9 meters. Can you guys visualize 9 meters? Meter is pretty close to what, like American unit. It's close to a yard. So visualize 9 yards and it's a little more. Okay, it's fine. 30 feet. I can picture that. So think again now. The Earth and the Sun in our scaled down version, like they're really far apart in reality, but in our scaled down version, they're like these two little points on the top of a pin, right on top of each other. 1 light year, which is an incredible distance, has been shrunken down in our scaled version. And how far is it? It's 9 meters. It's about 30 feet. So we've got the Earth and the Sun right next to each other. But how far can light travel in a year? From here to 30 feet away. That's how far light goes in a year. Okay? Which kind of makes sense. If the light from the sun can get here in 8 minutes, well, then light can travel a lot further in a year, right? Travel about 30 feet in this version of things. Okay, so now we get to fill in the table. That was just 1 light year. There isn't anything that's exactly a light year away from us, but we do have some light year things in the table. So let's try to fill out some of the stuff in the table. 4.4 light years is how far it is from the Earth to Alpha Centauri A. Jocelyn. You can. You guys see what Jocelyn's actually taking it. He's like come up with a really nice shortcut way. I'm gonna do like one more of these calculations, just like we've seen, just so we can really understand what's happening. But Jocelyn's got a really great shortcut that works. Okay, 4.4 light years. I can deal with that. First thing I can do is get it to kilometers. What was our kilometer light year conversion? It's right up above, actually. Yeah, right there, that 9.46 times 10 to the 12th. That's how many kilometers are in a light year. We've done that before. And I can multiply them and get some enormous number, but I don't really care about that number because we're going to scale it down. And in this example, how do we scale everything down? It's the same fraction we keep using, 1 over 1 quadrillion. That's how we shrink things down in this version. 1 over 1 quadrillion. You know the worst thing? I wouldn't be so annoyed by the power save mode. I know I'm harping on this today, but the problem is every one of these buttons works, except you know which one doesn't do anything? Oh, it works. Oh, it's fantastic. Oh, it never worked before. The on button never did anything. Second, then off if I want to turn it off, right? Second, and then off. Yeah, I can do that. No, but the on button, it never did anything for me before. Oh, this is super. Oh, wonderful. Even if the sun has disappeared in the last 8 minutes, I'm in a good mood. It's fine. Yes, we're going to do it. Let me do it the standard way, and then we're going to show Jocelyn's nifty trick. Okay, so I'm just typing all this stuff in. 4.4, and then 9.46, and then I'm using my E button. It's a nice shortcut, 12. And then divided by, what's our quadrillion number every time? It is 15 zeros. So let's move this out of the way. And we hit enter, and we'll get 0.04. Great. 0.04 what? It's kilometers. The light years disappeared, right? We converted to get rid of those light years. So all that was left was kilometers. When you shrink it down, it's still kilometers. So let's get our, what was it, 0.04? Is that right, 0.04? Kilometers. 0.04 kilometers. Okay, how many meters is that? Is that 40? Multiply by 1,000. Multiply by 1,000 to get meters. Yeah. So again, the Earth and the Sun right on top of each other, less than a millimeter apart. We go to the next closest star, Alpha Centauri. It's incredibly far away. Where is it in the scaled model? It's about 40 meters down. Divided by the 10 to the 15th. Mm-hmm. Mm-hmm. Oh. You guys are just so clever. I don't know how it's difficult for me to keep up with you guys. Divide by 1,000 is a really nice shortcut that Sam has come up with. Because what was the number for the quadrillion? It was 10 to the 15. And if you have 15 of them, 15 zeros on the bottom, and 12 on the top, then how many do you really have on the bottom? You only have 3, right? And so Sam has put this together, and it's always going to be that conversion for the light years, and this quadrillion business for the scaling. So yes, you can do exactly that. Take this number, hit it with the 946, and divide by 1,000. Man, you guys are on the ball. Okay, here's my standard way to do it. 0.04 kilometers is the answer. Jocelyn's nice little shortcut. If we take a look at the next page, we have already converted 1 light year. We figured out 1 light year was this 9.46 meters. Yes? Okay, so if 1 light year is 9.46 meters, then 4.4 light years must be 9.6 times 4.4. And of course, when we do the shortcut ways, you're not going to want to do any way that I suggest because my ways are way too long. What was it? 9.4? No, it was different. Oh, it was 9.46?
Yeah.
Okay. Oh, just 9.46. Okay. And so that was 41 meters because what we did was on the other page, it was meters. This was 9.46 meters in a light year. So we just calculated and figured out 4.4 light years is 41.6 meters. Yes, and that gives us the same. Yes, that gives us the same thing. Okay, by hook or by crook, can you guys spend the next 3 to 4 minutes, fill in as many of these as you can? You can try my way, you can try Jocelyn's shortcut, try Sam's shortcut. Just come up with some way to see if you can try doing these calculations. Justin.